Welcome. Today we're going to learn about related rates. Related rates are when one thing changes, another thing changes, because it's related. So we're going to talk about the steps to solve these kind of problems and then work through one example. They're story problems, so one of the steps in these is to understand what's going on, be able to translate words into ideas and formulas. So here's the steps I have. First step, read your problem. Be able to read it. That's actually not a big step. Many people tie steps 1 and 2 here really together. Reading is not enough. You have to understand. That doesn't mean you can go, oh, I've got it, I solved it. But you have to understand what's going on, what's changing, what kind of things are moving at what rate or with respect to something else. Just have some feel for it. Then, to help that out, you draw a picture. It's important this picture has a lot of things drawn on it. Everything should be labeled. Every relevant thing should be labeled. With a constant number if it's constant, and with a variable if it's not constant. Suppose something happens 4 seconds after now. Well, you can't just put down the value of the thing in 4 seconds, because if it's changing, it's not a constant thing. So you put down the variable everywhere you would. But if something never changes, you can put a number for that. Anyway, this will make more sense in the next example. Label everything. Find all the relationships that you need. In particular, there's one thing they're going to ask. They're going to say, find blah, blah, blah. You need to know any relationship that has with the other stuff. Or basically, find a formula for it. Take the derivative. And then after you've taken the derivative, plug in any values that are now known for the specific time or whatever. This is kind of vague. So let's do an example that has words. I'll read it off, and then you can think about it. So a firework shell is being shot into the air. It's being fired straight up from a mortar. You're 50 feet away from the mortar. It is rising at 100 feet per second. As you look at it, the angle between the shell and the ground keeps growing. How fast is the angle changing 3 seconds after the launch? Now, for this problem, we're going to ignore the fact that everybody has a height. So we're really talking about the angle between the ground and the shell, not between your eyes and the shell. So look at that, think about it, and hopefully it will make sense. Start working it through and drawing a picture if you can. Okay, so what's going on? Well, there's a firework being shot up in the air. Hopefully it's a very pretty one. But it doesn't really matter for this problem. Here's the ground. Here's the firework. I'm drawing the picture now. I've already gone past understanding. I'm into the drawing. And maybe you don't fully understand when you start drawing. The drawing might help you figure it out. The next thing we need to know is there's a firework going up. And here's the firework at a given time. And then we're involved. So we're going to be over here. Hopefully 50 feet is a safe distance. But regardless, the idea of this problem is that we're here and we're looking up. As we look up, as the firework keeps going up and up, that angle keeps growing. And remember I said we're not going to care about the exact niceties of how tall you are. We're just talking about the angle with respect to the ground. So that means we've drawn it, we need to label things. So, how far is this? It says we're 50 feet away. 50 feet. Does that change? No. So that's always 50 in this problem. What else do we know? That's almost it. But it's not it, really. We know this distance. Well, it changes, though, so we should use a variable. I'm going to use h for height. And I drew that there without even thinking about it. That's the angle. The thing we want to know is how fast is this changing at a certain point? Because this is changing, so this is changing too. Do we know this length? The answer is no. Do we need it? Maybe. Maybe not. Let's wait before we solve for it because we might not need it. We need to know what this is. We need to figure out how this relates to the pieces we have. Hopefully, in trigonometry you can look at this and go, there's some kind of trigonometric relationship. So I see that angle. This is the opposite over the adjacent. Opposite over adjacent is the tangent. So that means the tangent of the angle is the opposite over the adjacent. There's my relationship. I want to know how fast this is changing. I can take a derivative. So I do. Let's take a derivative. The derivative of tangent of theta is going to be the secant squared of theta. The derivative here, I'm going to rewrite this. There's only one variable and there's a 50. This is a quotient, but you don't need the quotient rule. So I'm going to rewrite this to make it look a little bit easier for you. It's 1/50th of h. Now, h is a function that changes. So we take its derivative. It's like an implicit differentiation. The derivative of h is not 1. It's going to be h prime. So the derivative here is 1/50th of h prime. I'm going to write that as dh dt. Now you might be thinking, oh, but wait, did that work? Because you just realized there's a mistake in this problem. Because I was very careful. I said h is changing. If h is changing as a function, it needs a dh dt. What else is changing? Think about it. We talked about it. What else is changing? Theta. I took the derivative of tangent of theta and I got secant squared of theta. And that's sort of right. But theta is not our variable. Theta is a thing that's changing with time. So what do we really need over here is not secant squared of theta. We need secant squared of theta d theta dt. I could write theta prime if you prefer. But I like to write it with dt because it shows t is really the variable. T is the time. How fast is this changing? Is it rate with respect to time? Therefore, this is the thing we want. If you forget that, it's impossible to solve for it because it's not there. That's the trickiest part of all of these, I think. Remembering that things that change have a derivative. Now, that's what we really want, is that d theta dt. So let's solve for it. D theta dt is 1/50th of dh dt divided by the secant squared, or another way of writing that is times the cosine squared of theta. So all we need to know is what these are. Now, this is rising at 100 feet per second. So 100 is dh dt. It says 3 seconds away, is that right? Let's see, changing 3 seconds after launch. So how tall is that? That's 300 feet, right? We don't actually need to know that for the problem. H is not in this problem, but the cosine of the angle is. So what happens? This is an angle. As it grows, the rate depends on what the angle is. This is like implicit differentiation. The rate of y changing depends on y itself. Okay, now, how do we find that angle? Cosine is what? Adjacent over hypotenuse. I can't use h for that, but adjacent over hypotenuse. Well, what is the hypotenuse? I have the side, this side, I can find that. This squared equals that squared plus that squared, or another way of saying it, this is the square root of 300 squared plus 50 squared. It's 90,000, and then 50 squared is 2,500. So that's 92,500 square rooted. So the adjacent is 50 over the square root of 92,500. But that's the cosine, so I want the cosine squared. So that square root is gone. That's nice. So d theta dt is going to be 1/50th of 100 times 50 squared over 92,500. There's a lot of little bits in here, so I'm going to come back to my handy dandy calculator and get a numerical value for this. I have 100 divided by 50. Okay, that's 2, I know that. So 50 squared times 2 divide by 92500 0.054054 ... What does that mean? Well, the units in calculus for trigonometry are radians. So it's 0.054 radians per second. That's how fast it's changing. Now, if you don't like radians, we can convert that to degrees. That's about 3 degrees a second. So that's how fast it's changing. Think about it, 3 degrees every second. It's not going to be 3 degrees every second because it changes as seconds go along. But hopefully you can see the key to this, understanding what's going on, drawing a picture, labeling, getting the formula, taking the derivative, and now plugging things in and working it through. Until next time, this is Dr. Chet.